Hello Internet! Looking at your comments on my last video, I thought maybe it would be a good idea to have a very short introduction to DGL, the Deep Graph Library Graph Construction, because there was some misunderstanding, because sometimes I refer to it as attributes, sometimes as features. We have some homogeneous graphs, we have some heterogeneous graphs. So let's go into the basic and define what I exactly mean. Now, we want to have a DGL graph construct. And how to do this, there are three ways. You import your DGL, you have your NumPy, you have your PyTorch, and then you simply say that your DGL graph, you have a node 0 to a node 1, from a node 0 to a node 2, from a node 0 to a node 3, from a node 0 to a node 4, and from a node 0 to a node 5. So the number of your nodes is 6. This is a way to construct a DGL graph. Equivalently, if you want to be absolutely precise, you have torch long tensors, so this works also. Or you can even commit the number of nodes if it is available from the edge list alone. Now, let's do this very fast. So to print the edges, the information you get, you have a tensor and a tensor, so from 0 to 1, from node 0 to node 2, from node 0 to node 3. This is it. But if you want, and this is the beauty, that homogeneous networks, you can transform to a NetworkX. So if your transformers and you let it draw you, well, you are not surprised at all that we have our node 0, and then we have our nodes 1 to 5. And we have clearly from 0 to 1, from 0 to 2, from 0 to 3. So this is exactly how it looks. In some time, I use the trick to visualize if it is just a low dimensional to get an idea how complex the graph is. Now, about features and attributes stored in the node and in the edge, the values and so on. Assigning node and edge features to a graph. A DGL graph only accepts attributes, information stored in tensors with the numerical content. So sometimes I call it attributes, sometimes it is called features. Please note features and attributes stored in tensors are the same thing. So no confusion there. And you have, of course, many graph data contain attributes on nodes and on edges. So let's have a look how to do this. You can assign and retrieve node and add features via the N data and E data to the node data and the edge data interface. For example, we have now our DGL graph G, and now we say, okay, assign a three-dimensional node feature vector for each node. Then you have simply this command line and you got it. If you want to assign a four-dimensional edge feature vector, now you see this is something different. For each edge, you can say, okay, it's some random 5, 4. Or if you're really going, yippee, you can assign a multi-dimensional feature matrix for each node, 6, 4, 2, for example. And then you have, of course, a different value. So have a look at this. And if I then say, okay, show me now from my DGL graph E data, the edge data with weight, we defined here the random 5, 4, we get exactly 5 lines with a 1, 2, 3, 4-dimensional matrix. So this is it. This is all there is to. If it is a higher dimensional, 6, 4, 2, we have 1, 2, 3, 4, 5, 6 blocks. And we have a two-dimensional, if you want, coordinate system, and we have 4 rows. So a 6, 4, 2 is very easily a multi-dimensional representation. Of course, you can have a look at your DGL graph. Remember, the DGL graph gives you the number of nodes, 6, the number of edges, 5, of course, because everything runs out of node 0. And then it gives you the N data and the E data scheme. We called it value and edge weight. So node value and edge weight, and you have a defined scheme. And when we went crazy and we refined a multi-dimensional, we defined also for the node data scheme value 2, and this is float 32. So as you know it, the number of nodes and the number of edges, you can directly ask them, or the out degree and the in degree of a specific node of our center node 0, for example, here, as you know it. Well, Matplotlib and NetworkX for visualization, or if you're working with a DGL backend, PyTorch, you can define it and do whatever you like to do. So if you then want to have an edge view, well, easily done. 0 to 1, 0 to 2, 0 to 3, 0 to 4, 0 to 5. You remember this. This is now our NetworkX representation. And what we have here is a multi-die graph. Multi-die graph, you remember, you can have then different commands, the views of the nodes. You can draw your networks, still the same networks. You can have a different function, kamada kawaii, or your edges. You even can say, hey, is there a shortest path from 3 to 1? And it tells you there's no path between 3 and 1 because from 3 to 1, we only have from 0 to 3 and from 0 to 1, but we have no edge from 3 to 0. So therefore, there is no path between 3 and 1. Yeah, you can have in a NetworkX presentation your multi-edge data view, heaven's sake, and you can assign whatever you want to it. But this is not so important. What I want to show you, you can of course do the reverse. We took a DGL graph and modified it to a NetworkX presentation. You can do exactly the same. You can have a NetworkX graph. This is your G of X. And then you define the node attributes, or the node features, sorry, or the add features. These are what we defined as value and weights. And then you simply say DGL graph from NetworkX. You put in your NetworkX graph and you get a DGL graph. So very easily done. This is the basic notification, how you construct this. And then you remember hetero graph, I never use this word. I always say inherently heterogeneous. We already had a look at this. We had, where is it? My data set, my ACM data set from the last video. I showed you that we have here quite a lot of data keys, as I called. And we have here, we have here a matrix presentation from the paper to author, from the paper to paper to V is, what is V? From paper, A for author, C for conference, L or T for subject code. Okay, so you have a lot of relation between the different nodes, between the different node features. But what we are interested in here is paper versus author, because kind of a citation, a knowledge database, a citation structure. And we see here, if we choose this one, we have 12,500 times 17,400, a sparse matrix of the type NumPy float 64, and 37,055 elements stored in the sparse column format. Yes, as already told, P stands for paper, A for author, and so on. And then we just pick a specific compressed sparse column matrix format. And this is paper versus author. So we have the paper, the author, and the links. And instead, you remember the number of non-zero values. So what we get is the number of papers, 12,500, the number of authors in our network, in our graph, 17,000 nodes, and the number of links between the nodes we have paper and the nodes we have author, and the links between these nodes, we have 37,000 nodes between our two types of nodes. Now we have the SciPy matrix and we convert it now to a heterograph, to a heterogeneous graph. Yeah. And this is easily done with a DGL command, DGL heterograph. The paper written by on the author. So we have paper, this is our node, the author is a node, and written by is our relation. We take the non-zero elements from our data. Paper publication versus author. And if you want to have a look at this, it is the same number, of course, the number of nodes. We have the author nodes, 17,500 author nodes. The paper publication nodes, we have 12,500 nodes here. And the number of edges, for paper written by author are 37,000. Yes. What is this? Ah, yeah. Here I wanted to show you that let's make an interrupt here. Just a short interrupt. I just wanted to show you that with the hetero graph, if you want to convert it to a NetworkX, we run into problems. So a very simple, this is the simplest idea you can have for a DGL hetero graph. You have user and node, and the attribute is follows. You have user follows another topic, and then you have user plays another relation, game another type of nodes. And you have defined your PyTorch tensors, and then you convert it in a hetero graph. So this is very easy. But if you now, so you have 5 games, 3 topics, and 4 user nodes, and the number of edges between user and topics is 2, between the number of edges between user follows users is 2, and the number of edges between users plays game is 2. And if you now try to morph this into your NetworkX representation, of course, there's an error, because DGL, Deep Graph Library to NetworkX, only supports homogeneous graphs. So we are here deeply into heterogeneous graphs. So remember, in a homogeneous graphs, all the nodes represent instances of the same type, and all the edges represent a relation of the same type. But we have here quite different relations, like example follows and plays. And our nodes has users, a topic, a game. So we are definitely, not a homogeneous graph. We are a heterogeneous graph. The node and the edges can have different types. And to NetworkX supports only the conversion for a homogeneous graph. And now you say, okay, so can I transfer my homogeneous graph, my heterogeneous graph, to a homogeneous graph? And the answer is yes, but of course you lose information. But let's have a look at this. You can simply define some data structure, and then you say, okay, imagine if you press it in a two-dimensional representation. With a big press, you squeeze it down and everything is pressed into a two-dimensional grid. Then let's have a look at this. You end up with 12 nodes. The number of edges is 6. This is exactly what we had before. You can have the number of nodes in this new squeezed presentation. And now, since we've lost some information, when we have now homogeneous graph, we can do now NetworkX morphing and a presentation of NetworkX in a two-dimensional plane, of course. And you see, this is the relation. Let me have a look at this. We can get it. There must be another, I guess there between 4 and 11, there's another one. Yes, here. So it's a better presentation. So we have, you cannot differentiate here what is the relation. This is a more or less all squeezed into the same level. So we cannot decide anymore. So going from a heterogeneous graph to a homogeneous graph, we lose a lot of decoding information. But just if you want to get an idea about the relation and not about the node structure that you encounter in your heterogeneous graph, sometimes this simplification of a visualization, I use it. Sometimes it's helpful, sometimes not. Well, it depends on your task. So this was the interrupt for homogeneous representation, morphing it to NetworkX. Now back to our original paper, where we have the number of nodes of a paper, of a user, and the reference. So you remember we have the number of nodes, 12,500. We have the number of edges, 37,000. And if you want to find the authors and all the authors of paper number 1, you know that here you have exactly the 4 encoded authors for the publication number 1. So, of course, a homogeneous graph is just a special case for a heterogeneous graph with only one type of node and edges. We know this. And then we select a homogeneous graph, paper citing paper with our non-zero data. And we have a look at this. The number of nodes, 12,500, the number of edges, 30,700. And we can create our hetero graph significant. And the following tutorial I take from this link. This is a very interesting text. It's a homepage, Cloud for Science.org. I leave you the link also in the description of the video. And the following code examples are from GitHub, DGL Graphs, Hetero Intro, a very nice Jupyter notebook. You find a lot more information if you're interested in this over there. Have a look at it. I give you also both links in the description. So you know that the examples of our multi-link structure is, of course, paper 0 was written by author 0, author 0, the author is writing paper 0, paper 1 cited paper 2, and paper 3 is about subject 1. So there are a lot of different types of links and different types of nodes. And if you want to find out a little bit about the basic of the graph, you have the n types. So our node types are author, paper, and subject. These are our three main type of nodes. And if you look at the node author, you see we have 17,430 entries here. Now, if you want to find the author by name, this is a very nice piece of code. It's just a function. You call this function with a particular name, and you get the encoded numerical representation by Jack J. Dongara. Beautiful. And if you want to find an institution of the author who published the paper, you have the same. For example, you're looking for Indiana, and then you have Indiana University and Indiana University, Purdue University, Indianapolis. If you're looking for a specific author, no problem. And if you're looking for subgraphs, like say example, you have your graph, your DGL graph G, and you want to have the subgraph authors writing the paper, can we extract this with our specific edge type. And you see these are the papers and the authors, and you know all of this. What else? When we ask which paper by a specific authors are included in the data set by looking for the out edges from this particular node of the author that represents the author, and having the idea of the end of the out edge, we can get the abstract of the paper. Because, of course, from the author, we have a direct pointer to the different papers the author has been written. So we get now a tensor with our encoding of the publication. So we go to a publication or to a paper matrix. We look up the specific data, and you see here we have now the text. B-object scheduling algorithm for optimizing mixed pattern heterogeneous, blah, 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 blah. Here we go. Beautiful. Again, further information. You can hand then also the written by subparagraphs to get the name of the co-authors of this particular. You see, he is this person, and these are his co-authors, or the subject classification of all papers we have available. So you see this particular paper, this particular thing was classified as being an object within C.4. So you can see it is very easy to get or to extract a lot of information from your DGL graph, the way you construct your DGL graph. Here I showed you two examples, a simple graph and a heterogeneous graph. We went through all the code. The link to the notebook I will leave you also in the description of this video. And I hope this answers some of the basic questions concerning the application of DGL. And of course, as always, this has been done on our free of charge Amazon SageMaker Studio Lab. I ran a GPU version only. And I hope you get some insights. I see you in the next video.